Good morning. That was 2 minutes, that's right. Okay, my talk is going to be on the ecology and nutrition of macroalgal blooms in the Indian River Lagoon. Dennis did a nice kind of setup for the talk. Why are we concerned about macroalgae? This is a shot from Brevard County just a couple months ago showing these thick algal mats that overgrow the seagrasses. So obviously they smother them, reduce the light. The green plant is Chetamorpha. It's a new kid on the block. We haven't seen a lot of that here yet, but we've had a lot of experience working with that. Down in Jamaica, some polluted areas around Negril where there's a lot of sewage. See the red plants here, these are Gracilaria. And the macroalgae are like the first responders to nutrient pollution in these shallow estuaries like the Indian River Lagoon. If you look at the schematic up on top, what happens when you increase nutrient inputs from changing land use into these estuaries, you can actually promote the growth of seagrass in the beginning. But as nutrients increase, macroalgae build up, seagrass epiphytes begin to overgrow the blades, and you begin to get more light limitation to the seagrasses. And at some point, a tipping point, you actually begin to get dense phytoplankton blooms like the super bloom and the brown tide. And at that point, you can undergo catastrophic loss of the seagrasses. And you can see the record of seagrass cover on the top right panel, how it's actually increased in decades up to 2010, 2011 with a precipitous decline. And this is kind of what the resource looks like, the bottom photos showing Haladuli going through an epiphytic stage to macroalgae to that end point. That's the brown tide over there. So the point is, we can learn a lot from macroalgae about the nutrition, the status of the Indian River Lagoon with respect to the sources and the levels of nutrients. And we did this beginning in 2011, 2012. Timing is everything. We just happened to begin this study when we reached this tipping point in the Indian River Lagoon, and we had the opportunity to actually capture the nutrient dynamics of what was happening. We, for the first time, did an Indian River Lagoon-wide study all the way from Ponce Inlet in the north to Jupiter Inlet in the south. 5 segments. I'm going to be showing the data: Mosquito Lagoon, Northern IRL, Banana River, Central IRL, Southern IRL, where we collected water for nutrient analysis. We collected macroalgae also for tissue nutrients, and carbon and nitrogen isotopes specifically to tell us what the source of the nitrogen is feeding these algae blooms. And we also looked at the seagrass cover in all these segments. The goal was to really lead to an improvement in water quality by providing user-friendly data to resource managers and policymakers. This is the chlorophyll A data, the amount of phytoplankton biomass in the water column. Again, the segments are along the bottom: Mosquito Lagoon, Banana River, Northern IRL, Central IRL, Southern IRL. I'm going to be showing several plots of data. But you can see we captured the super bloom at the first sampling, the dry season of 2011. This is when we were coming out of the extended drought. This followed kind of a first flush, a stormwater event in the lagoon. So we see that big peak of chlorophyll A. Normally the chlorophyll A levels in the lagoon are way down here. You can see how high the chlorophyll went in the Banana River. In our final sampling, you can see the brown tide. It went even higher, even denser populations of Oreoumbra lagoonensis, the brown tide organism. This is the reactive forms of nitrogen: ammonium, nitrate, nitrite, what we call dissolved inorganic nitrogen. You see the 1 micromolar threshold on the bottom. This is just to show you all you need to generate a bloom is about 1 micromolar. So you can see the entire lagoon is about at that level. You see the very high concentrations here in the central Indian River Lagoon. This is the Indian River County area. We have a lot of fresh water coming in. St. Sebastian River and the relief canals in Indian River County. Soluble reactive phosphorus, again, you see the threshold at the bottom, 0.1 micromolar is about all you need to sustain these blooms. You can see how high the phosphorus is up and down the lagoon. Again, highest values in the central IRL, right here where there's a lot of fresh water carrying these nutrients into the lagoon. Now the total dissolved nitrogen pool is a little different than the highly reactive ammonium nitrate. We think macroalgae are very responsible for the pattern we're seeing. The macroalgae, and there is about 3 times as much macroalgae as seagrass biomass in the northern segments of the Indian River Lagoon. They assimilate the reactive forms and they release dissolved organic nitrogen. And you see this trend here with very high concentrations of total dissolved nitrogen increasing as you go north in the Indian River Lagoon. Now, some of that nitrogen can be used potentially through cycling by these phytoplankton blooms, and that's something we're going to look at. But you see the 50 micromolar threshold. That's the IRL state target. So you can clearly see we need to get the nitrogen down in the lagoon. Total dissolved phosphorus, again, like the inorganic phosphorus, we see a lot right here in the central IRL. Again, coming in with the fresh water, and you can see it's over the IRL target of 1.7 micromolar. The N to P ratio, the relative amount of nitrogen versus phosphorus, you can see how it goes way up as you go into the northern segments of the lagoon, meaning those areas are pretty strongly phosphorus limited compared to the southern areas that are more nitrogen limited. That switchover occurs around a value of 30. And these are some of the macroalgae now that we used as bioobservatories. By collecting them and analyzing their chemistry, they can tell us a lot about the chemistry of the lagoon. Gracilaria tikvahi up here was the most common plant encountered, but these other red algae like Hypnea, Laurencia were also, and Acanthoph were also quite abundant. This is the carbon-nitrogen ratio of the macroalgae. A value of 12 is kind of a threshold above which you get nitrogen limitation. Point being, despite all the nutrients in the water, these plants grow so fast they can still become nitrogen limited. Very similar pattern with phosphorus. We see values very high, above 250, indicating very strong phosphorus limitation in the northern segments of the IRL. We see the same thing in the nitrogen and phosphorus ratio. Again, a very different scenario between the north and the southern Indian River Lagoon. Much more P-limited in the northern area. Stable nitrogen isotopes tell us a lot about the source of the nitrogen. Values above 3 increasingly indicate wastewater, sewage as the nitrogen source. Values under 3 get down in the fertilizer range. This red box shows the Indian River Lagoon. The overall average was 6.3, very similar to Boston Harbor that sees a lot of sewage input. That's the bad news. Roberts Bay over in Sarasota Bay, very sewage polluted body of water as well. If you look at the far right, Florida Bay, that's also suffered from algae blooms for many years, but look how low that value is, down around 2. That's agricultural nitrogen, that's fertilizer nitrogen. This is the power of this technique to really be able to fingerprint the source of nitrogen. And we're actually trying to focus in Indian River County, look more closely at the delivery of the nitrogen from the relief canals, 36,000 septic tanks that are draining into these canals, discharging out into the lagoon. This work's being done by Marie Tarnowski, collecting a lot of data relevant to on-site sewage disposal systems. During our study, the manatees began dying. We're working with Dr. Peter Muller up at the Noah Hollings lab. He's already isolated these toxic cyanogenic glycosides. Going to be wrapping that work up soon. Seagrass cover versus nitrogen. This is basically showing the Haliduli radii, the blue bars, during our 3 samplings. And you can see the decrease over time. The black dashed lines are the total nitrogen, being high in the northern lagoon and decreasing as you go south in each of the 3 samplings. And it's interesting, if you look at the other seagrasses, Halophila, Syringodium, and Thalassia, you see we really only find those in the central and southern IRL where we have better water quality and lower nitrogen in particular. And you see that orange bar is a threshold we determined for turtle grass, Thalassia testudinum. It does not do very well in environments with higher nitrogen than that. And you see that model developed in the Florida Keys works quite well in the Indian River Lagoon. We're taking that one step further. Dennis pointed out the importance of light reduction to seagrass decline in the lagoon. We all assume it's reduced light causing the die-off. We're actually getting empirical data with carbon isotopes. These are data showing the Bahamas, the black dots, the clear dots are the Florida Keys. Those red dots are the Indian River Lagoon. These plants become depleted in the Del C13 content of their blades under light limitations. So this really shows how light limited these plants are. With that, I'm going to wrap up, and I owe all this to my wonderful team, the Team HAB, who are out there in the Indian River Lagoon right now sampling. Thank you.